Good morning, everyone. My name is Ivan, and I'm from the Chinese University of Hong Kong. And I work with Professor Samuel Au and built this robot called Bruce. I believe most of you have seen the robot demo during your DLR visit. And I've received a lot of questions. Hey, this is a really nice demo. And then the question is, how did you get to work with the DLR? So I just want to clarify that I'm just a master student from Hong Kong. I'm not really lucky enough to work with the DLR. I'm just here to present my robot. All right, let's go. So I believe most of you have seen this already. So our motivation is to use a really simple solution to capture animal mobility, extreme agility. So our major inspiration is from this video, which I believe is from Professor Clark in San Diego State University. This is the evasive survival behavior of a kangaroo rat in a desert. So as you can see, as the snake attacks the rat hops up and kicks the snake and then hops away. So there are several qualities that we want to capture from this, which first of all is, of course, high power density, a really lightweight rat that can hop really high, and high aerial maneuverability, the ability to rapidly adjust its aerial orientation and redirect itself. And of course, high leg dexterity. You need to be able to abruptly point and apply force in multiple directions. So that's why we designed Bruce, which is composed of an omnidirectional collapsible leg and a telescopic propeller system. So the leg is mainly for the hopping motion and the thrust for hopping high, and also the landing robustness, while the telescopic propeller system is mainly for the flight phase, rapidly accelerating the robot and dissipating the energy. So one thing I want to mention is the leg is highly inspired by the GOAT robot. The parallel topology is introduced in this paper, but we did make some adjustment, including changing the leg topology slightly to make it analytically solvable, and redesigning the spherical joint to remove an internal singularity. So I believe it's best if I just show you the result to see the effect of the telescopic propeller system. So this one is on your left-hand side, the propeller is not turned on. So you can see as the robot can rotate a maximum of 90 degrees, and with the propellers on, it gained a lot of angular momentum and can complete the entire flip. And we have done multiple trials, I think dozens of trials with the flipping. So it's pretty robust despite what might happen yesterday. So this is another feature, quality that is of using the propeller system is the landing robustness. So after an extremely agile motion, you often have excess energy or excess angular momentum. So on your left-hand side, you see without the propeller to damp out the extra energy, it's very easy to trip over. While on your right-hand side, with the propeller, the robot can actually decelerate itself and make it land properly. So with this ability, we attempt to push the limit of the robot. That's why we did the double flip experiment, which achieved one of the highest angular velocity in hardware implemented robot. And also the Bruce Lee fly kick, which is one of the first and quite difficult to do so because the impact on the ball is really unpredictable and irregular. So we really rely on the propeller system to correct the flight trajectory afterwards. Yeah, so this is the double flip. Also, we have done multiple trials with the double flip. You can see the body trajectory on your left hand side and the foot trajectory on the right hand side. And for the flying kick, we have done multiple trials on free hopping height, 0.8 up to 1 meter. You can also see the trajectory right here. And finally, the consecutive forward and backward flipping, which is more difficult than it seems because we only have 2 hops to stabilize the robot before we take off again and do another flip. So one point is, why don't we use inertial approach like flywheels or tails? First of all, they're limited by workspace and motor speed. For flywheel, eventually the motor will saturate. And for tail, you have limited workspace on your joint. You can't just keep doing like this, right? So, and also the weight. The propeller is extremely lightweight, rating 30 grams, and the robot is 3 kg. So finally, I want to thank you, my professor, Professor Samuel Au, and I would like to show you the future of this robot. We are trying to extend the robot into the 3D space. And this is the preliminary trial with the 3D hopping without propeller. This is just the leg. So while this video is playing, I suppose I'll answer your question. Yes.
We have about 2 minutes for questions and then a few announcements.
What kind of actuators do you use on the legs?
Oh, it's a brushless drone motor with a 1 to 5 gearbox.
In the flying kick demo, it looked like the physical location of the propellers were fixed, but in all the other ones, you could translate them.
Yes.
Are you doing any inertia shaping or anything like that, or?
No, the telescopic mechanism is mostly just there for mimicking the kangaroo rat because they extend their arm when they're in mid-air, but there's no actual functionality from that.
More curiosity question, how often do you break the robots?
Too often. So, yes?
Can you show the fly kick again?
Sure, of course.
You're a little bit too fast.
There you go, should be this one.
Slow motion.
So what exactly, are you just hitting it or are you doing something special with the leg? And how much does it decelerate or break your rotation?
Oh, I've tried. So back when I was first tuning the robot, right after the kicking, I didn't do anything. I just let it. I just want to see the response, and it just dropped vertically onto the ground.
Okay.
After the
Doesn't
kicking.
you're not kicking explicitly, you're rotating it and hitting it on your way?
I at first accelerate the robot and then kick. Once that kick, pretty much all of the angular momentum are dissipated. So I need to use the propeller to accelerate the robot again to the other side.
Thank you very much.